All right, so this week we're going to finish up with 6.1. So we're going to be looking a little bit more at angles, and specifically we're going to look at something called angular velocity, okay, which measures the speed of an object spinning in a circular motion. Okay, so a unit you might use for that or you've heard of would be like RPMs, revolutions per minute. All right, so we'll talk more about how we can convert between angular and linear speed. So that'll be the big thing in 6.1. And then in 6.2, we're going to take a look at, what are we doing? Unit circle. Okay, so we'll start unit circle and we'll finish it on Monday. All right, so one thing we're going to look at first before we do angular velocity is what is called arc length. Right? There will be some questions on the test with this. And the arc length basically measures part of a circumference. That's an arc. It's part of a circumference of a circle. And we want a formula that can help us to figure out the length of an arc. Well, the first thing to understand about the connection between the size of an arc and the size of an angle is that they are directly proportional. So if I had, say, something like this, and I draw an angle that's 90 degrees, the arc that corresponds to the 90-degree angle would look just like that. Okay, so that's for 90. Now, if I do the same thing, what would be an angle that's double the size? How much would that angle be? 180. That would be 180. So there's my initial, there's my terminal. And the arc would be what I just drew in red. So I doubled the size of the angle. What happened to the size of the arc? It doubled. That's what directly proportional means. It means however you change one thing, the other thing changes exactly the same. If you made the angle half as big, the arc would be half as big. If you made the angle 4 times as big, the arc would be 4 times as big. Okay? That's directly proportional. And the size of the arc is really going to depend on two things. First, it depends on how big of an angle do you have, and how big of a circle do you have. Because just because you have a 90-degree angle doesn't mean the arc is always the same size. I could have a circle like this, and I draw a 90-degree angle, and now my arc is that big compared to the one up above where it's much bigger. Okay, so the arc length will depend on two things: the radius of the circle and the angle that you make in that circle. All right, so because arc size and angle size are directly proportional, we're going to be able to set up a proportion. Okay, anything that's directly proportional, you can set up a proportion to try to solve a problem. And what I've started out with here is a circle with two angles. I've put theta and s. S is the arc that corresponds to angle theta. S1 is the arc that corresponds to angle theta 1. Now, we're going to do the same kind of thing we mentioned before. We have to figure out a connection between arc size and angle size. Just like a connection between inches and feet. 1 foot equals 12 inches. Once you have something to start with, you can use that in your proportion to figure out anything you want to know. So if I had, for example, 12 inches equals 1 foot, and then we had something like x inches over y feet, and you wanted a formula to convert, feet to inches or inches to feet, all you'd have to do at this point is cross multiply, and you'd have 12y equals x, and that's one way you could write the formula, okay? Where x is inches and y would be feet. So if you had, for example, 8 feet, you could plug in an 8 for y, multiply by 12, and it would convert it to inches. Or you could use it the other way around. If you had 115 inches, you could plug it in for x, divide by 12, and it would give you y. Okay, but the whole key is starting with something you know. It doesn't matter the two things you put here. It could be a 2 and a 24. It could be a 10 and a 120. As long as it's a fact that's true. That's all. So, we have to start off with a fact that is true here. And I'm going to give you a hint. And let's suppose that theta 1 was 1 radian. Okay. Just like supposing, let's work with 12 inches. Now you tell me what 12 inches is, and you would say it's a foot. Well, let's suppose theta 1 was 1 radian. If this angle right there is 1 radian, then it automatically makes this arc a certain size. Does anybody remember what we said about that? If that angle is 1 radian, then that arc is the same as something else. Yep?
The radius.
The radius. There's our connection. If that angle is 1 radian, then the arc is automatically equal to the radius. So this is like having your 1 foot, 12 inches. Okay, so now what we're going to do is we're going to set up a proportion. Let's put what we know, okay, on the left. And we know that if we let theta 1 be 1 radian, then S1 would be, actually, you know what? Let me even set it up simpler first. Before I even plug anything in, let me just set up a proportion and then I'll plug some numbers in. So you can set up a proportion many different ways, as long as you're consistent on each side. We have 4 things that I just circled, and we have 4 spots to put those in a proportion. Let's start with the S and the theta. Let's do S over theta on the left. And then if I do that, what would have to go on the right if we follow the same pattern as the left? Yep?
The S1 over theta 1.
S1 over theta 1. Now, let's fill in what we know. Okay, the S and the theta, we don't know. Okay, that's going to be like this side of the proportion. You have to put the stuff you don't know on one side. It doesn't matter which side. Okay, so that's the stuff we don't know. So we have S over theta equals. And now on the other side, you have to put your conversion, you have to put your fact that you know is true, that connects the two things. All right. So the fact that we know is true from the definition of a radian is that if this angle is 1 radian, then the arc length equals the radius. That's part of the definition. That's automatic. Yep.
How do we know that S over theta is equal to S1 over theta 1?
Because they're directly proportional. So as long as two things are directly proportional, you can set up a proportion. If they weren't directly proportional, then you wouldn't be able to set it up. And you could set this up different ways. Instead of doing arc over angle equals arc over angle, you could do angle over arc, but then you'd have to do angle over arc on the other side, as long as you set it up consistent. All right, so we know that if our angle is 1 radian, then that would force the arc length to be the same as the radius. All right, and our goal now is to get S by itself. All right, so what would I have to do in that equation to get S by itself? John? Yeah, really, just multiply. You can cross multiply, but you don't even need to do that because when you cross multiply S times 1, you're just going to get 1. So just multiply both sides by theta. And the way we usually write this formula is S equals R theta. That's the formula for the length of an arc. You don't have to put divided by 1. S is the length of the arc. R is your radius. And theta is your angle. But we assumed something about this angle way back. What did we assume about theta? Okay?
That was 1 radian.
That it was 1 radian. Okay, just like in this formula, we assumed that we were working with inches and feet. So that means when you want to use the formula you came up with, it only works for inches and feet. This doesn't work for centimeters because that's not one of the units you originally assumed you were working in. Well, we assumed we were working in radians. That means when you use this formula, your angle has to be in radians. So that's where it'll tie in with what we did yesterday. If you have something in degrees and you want to use the arc length formula, first step, change to radians. All right, so let's find the length of an arc in a circle that has a radius of 2 and it has an angle of pi over 4. Is the angle they gave me radians or degrees? It's already radians, doesn't have the little circle on it, so I don't have to worry about converting it this time. And they gave me the radius, which is 2. They can give you any 2 of these variables. If they give you the r and the theta, you're going to solve for s. If they give you the s and the r, you're going to solve for theta. But the point is, there's 3 variables. You'll always know 2. All right, so let's just start by writing down the formula. Someone remind me, what's the formula to calculate arc length, John?
S is equal to theta times r.
S equals, yep, I'm just going to write it as r theta. Now fill in everything we know. Caleb, do I know S?
No.
No. Find the length of the arc, that's the question. So we don't know that. Okay. Madison, do I know R?
Yes.
Yep, and in this case, what did they give me for R?
2.
Yeah, so they gave me R is 2. And Sophie, did they give me theta?
Yes.
Yep, what is it? Pi over 4. So when we reduce that as much as we can, that's pi over 2. And what did I just find? Pi over 2 is the what? John? Matt?
Arc length?
That's the arc length. So what should I put for a label on that? Yeah? Inches. Okay, I can't tell you what the length label is always going to be. It depends on the problem. But when you're finding a length, you should always use the label that they used for length. There are 2 variables in that formula that measure length. One of them is S, one of them is R. The third variable measures an angle. So the answer there is pi over 2 inches. If they asked for a decimal, you could type it in. It's about 1.57. Question? Yeah.
Pi over 2 is 90, correct? Degrees.
If that was in reference to an angle, it would be 90 degrees. But in this case, it has nothing to do with being an angle. It has to do with the number 1.57 inches. But yes, it would be. Okay, questions on that? All right, let's try this one. A little different. I'm not going to go through every combination, but this time they're asking you to find the radius, and they're telling you the arc length and the angle. All right. So, Lindsay, what's my formula that I'm going to plug everything into?
S equals R theta.
Okay, so S equals R theta. And Annalise, do I know S?
Yeah, it's
Okay,
3
what
pi.
is it?
3 pi.
3 pi. So we can fill that in. Okay, Nick, do I know R?
No.
Nope, that's the question. Find R. And Leanne, do I know theta?
Yeah.
Okay, what is it?
60 degrees.
So where would I plug that in?
Next to the R.
Okay, I do agree that an angle is going to go next to the R, but not 60. Do you know why we're not going to put a 60 in there?
Because it's in degrees.
Because that's in degrees, and what does our angle have to be in?
Radius.
Has to be in radians. So off to the side, we can convert that. What do I multiply by to convert that? Yep.
Pi over 180.
Pi over 180, and you're going to get pi over 3. Okay, so now we have a fraction next to our variable. We can get rid of the pi and the 3 at the same time by doing something on both sides. Does anyone remember what you can multiply both sides by when you have a fraction next to your variable? Nick?
Denominator?
So can you tell me here what I would multiply both sides by?
3.
Okay, you could multiply by 3, but you're still going to be left with the pi there. We can get rid of the pi at the same time, and multiplying by 3 is part of it. Yep.
You could do 3 over pi.
And what's that called? Yep. The reciprocal. Okay? Just like if you had 2/3 x equals 12, you could multiply each side by 3/2. You could multiply by 3 and then divide by 2 separate. But if you want to get rid of both in the same step, multiply by the reciprocal. 3 over pi. 3 over pi. That's gone. That's gone. Let's see. That's gone. And all we're left with now is we had 3 pi, and we're multiplying it by, let's see, 3 over pi, so the pi's are gone, so we're left with 9 equals my radius. What should be my label on that?
Feet.
Feet. 9 feet. Any questions on using that formula? Okay, the only variation we didn't do was solving for the angle when they give you the s and the r. Okay, but you just take s, divide by r, and that would be your angle. All right, so that's the first part of this section, the arc length. The second part is on what we call angular velocity. So angular velocity is basically used to measure the speed of something spinning on a circular path. You can call it angular velocity or angular speed. It's the same thing. Now, it says there you can use radians, but there are actually 3 units that you can use to measure the speed of something spinning in a circular path. You can use radians, you can use degrees, or you can use revolutions. All 3 of those units measure angular velocity. If you have a problem and it doesn't tell you what units to use, let's say the problem just said find the angular velocity and then they give you a problem. The default unit to use will be radians. Okay, that's why I wrote radian measure. So when they don't specify a unit, use radians. Now, since it's a speed, speed is always something per time, like miles per hour, feet per second, feet per minute, right? There's always a time unit involved. I don't care what time unit you use. Time unit can be whatever the unit they give you in the problem is. So if they give you seconds in the problem, you could find angular speed in radians per second. If they give you hours, you could do radians per hour. The only time you have to change it out of radians if they said something like find the speed in revolutions per minute. Well, now they're telling you not to use radians. You have to do revolutions. Okay. So let's take a look at an example. And I'm going to spin these 3 dots in a circle. So whenever something's spinning in a circle, you should use angular speed to describe it. But I'm going to try to use linear speed. And let's see what happens. What's the formula for linear speed? We did this when we did the train problem. We had somebody in a train, and they got in a car or something. It was distance equals what? Yep.
Velocity times time.
Yep, velocity times time, or rate times time. So if we wanted to solve this for rate, what would it be if you solved it for rate? Yep.
D over T.
D over t. So let's spin these 3 dots in a circle and let's watch what happens. Okay, they're all grouped together. And I'm going to spin them one time, just like that. How long did it take each dot to go around one time? Like compare the inner black one, the red one, and the outer black one. How did the time compare for each of those dots to go around one time? Michael?
It was the same.
They were all the same. So each one of those dots did its thing in the same amount of time as every other dot. But which dot traveled the farthest? Yeah? The outermost one traveled the farthest. So what does that mean if this dot on the outside traveled farther than these other dots in the same amount of time? The outer dot traveled further in the same time. Bigger numerator than any other one. Michael?
It was going faster.
So it must have been going faster. The only way you can cover more distance in the same time as somebody else is if you go faster than they do. And that's what gets confusing about trying to apply linear speed to something spinning. Every single point on that disk is traveling at a different linear speed as you travel out from the circumference. The closer you are to the middle, the slower the linear speed is. The further out from the middle, the faster the linear speed. So that gets confusing. So now we're trying to describe the speed of something spinning, but now we have to say, well, what part of it? Like the outer part of it, or the middle part of it, or the center part of it? And actually the center part almost has a speed of 0. If you think of this dot as not moving at all, it has 0 distance divided by time. That means this is not moving. It's 0 speed. So the way we can get around that and not have different speeds for all these dots on the disk is to describe it using angular velocity. I could say that every dot on this disk made 1 revolution in, say, 2 seconds. And that would be the speed. 1 revolution in 2 seconds. Or a half a revolution per second. I could say it that way too. And that's the same for every dot. All right, so that's why we use angular speed. So let's take a look at an example. I already mentioned this to you guys, that angular speed is radians per time unit. Again, I don't really care about the time unit, whatever the problem is. But I do care that you use radians unless otherwise specified. So linear speed, that's a little bit different. Okay, that measures the speed of an object moving in a straight line. And units we use for that are units that you would use to measure the distance between 2 points. You wouldn't use revolutions or degrees or radians to measure the distance from here to, say, the back wall. You wouldn't say it's 6 revolutions from here to the back wall. That doesn't make sense. But you could say it's 6 feet, or 6 miles, or it's 6 inches. Right? Kilometers. Those are all units you can use for linear speed. And the way we're going to convert from angular to linear speed is pretty much the same way I showed you how to convert between degrees and radians. I always ask you, where do you want to put the unit so it cancels out? And that's what we're going to think about. We're going to have fractions. The numerator and denominator are going to have units. And we're going to say, okay, we don't want minutes, we want to get hours. We have minutes in the top. Where would minutes go to cancel out? It would go in the bottom. And that's how we'll do it. So there are basic things you do need to know that I would not give you on a test. You should know all the conversions between basic time units. Seconds to minutes, minutes to hours, hours to days, days to years, regular year. You should know basic length conversions, inches to feet, feet to yards, feet in a mile, things like that. Now, if it was a conversion like between inches and centimeters, that's kind of a weird conversion. Now you're going from standard to metric. So that would be a conversion I would tell you. Okay, let's try this one. So this is just a conversion that's not even a rate. It's just part of a rate, specifically the time part. Okay? So it's just 3 days. If you want to think of it as a fraction, we could just put it over 1. Now, I want to convert days to minutes. So we're taking a big unit and we're making it into a smaller unit. What's the next unit down from a day? What is it? Hours. So I want days to cancel out, and I'm going to first convert to hours. Because I can't convert right to minutes, because I don't know how many minutes in a day off the top of my head. I know how many hours in a day, that's easy. So I'm going to go to hours first. Where would days go to cancel out? Top or bottom? Yep, bottom. So we're going to have days in the bottom. We're going to have hours in the top. And now we have to fill in the conversion. There are 24 hours in one day. All right, so now days is gone. Now we want to cancel out hours. What's the conversion between minutes and hours? Michael?
60 minutes per hour.
60 minutes per 1 hour. Where is hours going to go this time? Top or bottom? Bottom. So we're going to put hours in the bottom. We're going to put minutes in the top. And there are 60 minutes in 1 hour. Hours is gone. And now look at your units and see what you're left with. Minutes over nothing. That's what you want. Now we just multiply straight across. So 3 times 24 times 60. Okay, so the answer is 4,320. Questions on that? All right, so that's just a time unit. Now let's try converting a rate. So a rate has two labels in it. It has not only a time unit, but it has a distance unit. So let's convert feet per second to miles per hour. So now it's like we're going to be doing 2 problems. When they say 50 feet per second, what does that mean? 50 feet in how many seconds? 1. It's 50 feet per 1 second. Now we can choose which one we want to deal with first. Let's get the seconds to hours out of the way, and then we'll come back and do feet to miles. Okay. We're trying to get rid of seconds, and let's go up to the next unit from a second. Where would seconds go to cancel out? Top. And what's the next unit up from a second?
Minute.
A minute? And what's the conversion between minutes and seconds?
60 seconds in 1 minute.
60 seconds in a minute. Now if you stop there, you would have an answer in feet per minute. John, can you just sign back in for me? Oh, all right, now we want minutes to go away because we want to get hours. Where would minutes go to cancel out? Top. Hours goes in the bottom. And what's the conversion between those two? Caleb?
60 minutes per hour.
60 minutes per 1 hour. If you stop there, you'd have a speed of feet per hour. We want to get miles per hour. Even if you don't know how many feet in a mile yet, you will need that. You should know where feet is going to go. Top or bottom? Bottom. Feet goes in the bottom. Miles goes in the top. And how many feet are in 1 mile? Yep.
5,280.
Good. 5,280. Feet. Feet. Now look at the units we're left with. Miles in the top, hours in the bottom. Perfect. Miles per hour. Okay, just multiply straight across. So we've got 50 times 60. Times 60 again. So that gives me 180,000 in the numerator, divided by 111, and then just 5,280. 280. All right, so that's a speed of 34.09 miles per hour. And that's one that sometimes you see mph. You can also write it miles per hour. Same thing. The two units that I usually see a lot, mph for miles per hour, RPM, revolutions per minute. Okay, questions on that one? All right, last one. So I want to convert, actually is this the last one? Second to last one. I want to convert 200 radians per second to revolutions per minute. Okay? So now we're just doing exactly the same thing we did before, but we're using some units that might be a little bit less familiar. All right. Can somebody kind of walk me through what the first thing I could do is? Tim?
You can multiply by 60 seconds in 1 minute to
Yep.
every seconds.
So we could do 60 seconds in a minute, so that's good. So now you've got radians per minute. And I have one more step. Yep.
That would be revolutions over
Revolutions over what?
or the rad. Oh my god, I feel the RAD.
Yeah, what's the RAD stand for?
Radians?
Radians.
Makes it radical.
Now what's the numbers I'm going to fill in there? Nick?
1 revolution for 2 pi radians.
1 revolution for 2 pi radians. And now we just multiply it out.
How do we know the... Never mind.
Any questions on that? No? Yeah.
You just divide 200 times 60 by 2 pi. And that's how you get your answer in revolutions per minute.
You're going to take, 200 times 60. We get that. And then we're going to just divide that by 2 pi. So that's going to give me... I must have typed something wrong. When you divide by 2 pi, it can't get bigger than the original answer. 200 times 60 divided by, I probably need parentheses. That's probably what happened. Probably divided it by 2 and then multiplied it by pi. Yeah. Because I knew I couldn't divide by 6.28 and get a bigger number than I started with. So that's 1,909.86. And that is revolutions per minute.
You see fixed matter, not like...
No, we're just going to go to 2 decimal places.
Okay.
So far, we haven't really converted between angular and linear. That's the last step. Okay, so that's converting between 2 different types of speeds. We started in angular, we ended in angular here. We started in linear, we ended in linear. Now, we're going to start in one, but end in the other. So, I'm not going to do part A to this problem because we've basically already done that. All they're asking you to do for part A is to take a speed that's starting in revolutions per minute and change it to radians per second. Well, if we go back up to here, we had a speed that started in radians per second and we changed it to revolutions per minute. It's the same thing, except the other way. All right. So they're giving you revolutions per minute and they want radians per second. That part is just changing an angular speed to a different angular speed. What I want to take a look at is part B. I want to find the linear speed, and I have to be specific, of a point on the circumference. So basically, let's pretend like this tire was on like a machine and it was spinning at 1,850 revolutions per minute. If that tire fell off the machine and hit the ground, it would instantly take off going straight. I want to figure out how fast it would be going. So assuming it didn't, lose traction or tip over, it hit the ground and all the energy that it had from spinning went into making it take off and go straight. That's what we're going to figure out. And any time that you want to jump from angular speed to linear speed, revolutions is always the unit you want to be in to make that jump. You don't want to be in radians per whatever. You don't want to be in degrees. You want to be in revolutions. So let's start with that. 1850 revolutions per minute. Now, converting minutes to seconds, that's easy. Okay, we'll do that after. But what I'm more interested in is converting revolutions to feet. So, what's a revolution? Can someone describe that to me a different way? Like if I can give you a hint if you don't get it, but yeah.
Going in a circle once.
Right, it's really like a circle going one time, right? So, like let's say here's a tire, and here's a point on that tire. And let's say you take that tire and you roll it one time until it lands over here, back where it started. That tire would have rolled from here to here. If it rolled exactly one time. That would be one revolution of the tire rolling. How would you figure out that distance in red? It's something about the tire. Yep. It's the circumference. Right. So if you were to take this, if this was like, say, a metal wire, and you could cut it. If you could cut it right there and lay it flat, that would be the circumference of the circle. So in order to figure out the next part, which is how many feet in a revolution, you basically have to figure out the circumference of the tire, because the circumference is a revolution. So we're trying to find this distance in red. What's my formula for circumference? John? Caleb?
I think it's 2 pi r.
Circumference equals 2 pi r. What was my radius in this case? Yeah.
I think it was 18.
18 inches. Okay. Well, they want feet, so I'm not going to be able to get feet right away unless I want to convert 18 inches to feet. I could do that right now. What is 18 inches in feet? It'll just save me converting it later on. Yep. 1.5. You just divide it by 12. If you don't want to do that now, you're going to have to do it later. Okay, so 18 inches is 1.5 feet. So now I can say, let's leave our answer with a multiple of pi. What's the circumference of this tire? So 3 pi feet. So the circumference is 3 pi feet. Now I know how many feet are in one revolution of this tire. There are 3 pi feet. If you were to take the tire and roll it on the ground one time, it would roll 3 pi feet. So there are 3 pi feet in one revolution. And now you've made the conversion from angular to linear using the circumference formula. So the number of feet in a revolution is not a standard conversion. You have to figure that out every time. It's not like how many seconds in a minute. That never changes. But how many feet in a revolution depends on the size of the tire. All right, so we got that. So feet per minute. And what's the last conversion that I would need to get the answer they want? Mabel?
1 minute over 60 seconds.
1 minute over 60 seconds. Minutes is gone, and now my units are feet per second. All right, and that's probably the hardest type of problem from the angular to linear stuff, where you have to involve circumference. All right, so let's multiply 1850 times 3 pi. So 1850 times 3 pi. And we're going to divide that by 60. So if we had an object that was spinning at 1,850 revolutions per minute, and it had a radius of 1.5 feet, that would be equivalent to 290.6 feet per second. 290.6 feet per second. Yeah, I think 88 feet per second is about 55 miles an hour. So that's over 3 times faster than 88. So that's over 160 miles an hour. That's pretty fast. Just estimating. Okay, any questions on that? All right, so that finishes up the end of 6.1. And the last topic that will be on the test is unit circle trig. So we'll start it today and we'll finish it next time. We don't get into a lot with it today, so just a little bit.
We have more on 6.2.
Yes, there'll be 6 questions from this section. 6 questions. Okay, so the whole idea of unit circle trigonometry is that if you draw an angle in standard position, that means your initial side is here, your terminal side could be anywhere, but the terminal side is going to hit the edge of the circle somewhere. Okay. And let's assume that this is your origin, so that coordinate would be 0, 0. This point where the terminal side hits the edge of the circle, let's do a different color, or not. That point has a coordinate to it. In this case, the x value would be negative and the y value would be positive. Now, no matter where you draw the terminal side, it'll hit the circumference of the circle somewhere, and there is a location of that point. We can find it. It's a coordinate. That's the whole key of unit circle trig. That's the whole point of it. You have to be able to figure out a coordinate that corresponds to an angle. Okay. For the side in green, this is your angle, and whatever the coordinate is of that point, that's the x and the y value of the point that correspond to that angle. Okay. For the one that I did in red, that's your angle, and this would be the point that corresponds to that angle, and that point would have an x and a y value. Some points are easier to find than others, but that's what we're going to try to figure out. So, any questions on the goal of unit circle trig? Finding the coordinate for where the terminal side hits the edge of the circle, and that's the coordinate associated with the angle. I think I write that down right here too. Okay, so yeah, so for certain angles, and by certain angles, I mean angles that are multiples of 30 and 45. The unit circle isn't something we would use for just any angle. It's really only used for 30s and 45s. And it's a very important concept for calculus. Right? If you don't know the unit circle when you get to calculus, you're going to get very stuck with very basic trig problems.
What does the rest of that say?
So for certain angles, again, multiples of 30 and 45, we can draw them in a unit circle, and then we can sketch that arc, just like this. Well, that arc is going to hit the terminal side of the angle at a coordinate. The end point of that arc is where the terminal side hits the circle, and that's the goal of what we need to find, the x and the y. Those two values, the x value and the y value, will allow you to find all 6 trig functions. We're going to learn what those are in a minute. But if you can't figure out the coordinate, then you're not going to be able to do unit circle trig. Now, I keep saying the word unit circle, and I think I put the definition of that up on the board either yesterday or probably the day before. Does anybody remember what's the definition of a unit circle? Tim?
So just the radius is 1 unit.
The radius is 1 unit. So, knowing that the radius in this circle is 1 unit, I should be able to just move this stuff away. And let's write down some coordinates. Wow, I traced that one a lot. Okay. So let's write down the coordinates for 4 pretty common angles. That's the origin. So what would be the coordinate of this point if it's on the edge of the circle, and you know the radius of the circle is 1, so it's only 1 unit in every direction. We just have to take into account going right 1. And that's the coordinate for 0 degrees. Yep.
1, 0.
Coordinate for 0 degrees is 1, 0. How about the coordinate for 90? Caleb?
0, 1.
That would be 0, 1. And the coordinate for 180? Yep.
-1, 0.
-1, 0. And what's the angle that's down here, which is 3/4 of the way around?
270.
270. And what would be the coordinate for that? Sophie?
0, -1.
0, -1. That never changes. Those are always the 4 coordinates on the unit circle for 0, 90, 180, and 270. Those are called the quadrantal angles. So if I said to you, what's the x value of the coordinate for 180 degrees on the unit circle, you'd say -1. So those are the easiest because they all have a 1 and a 0 in them, or a -1. That's all the coordinates we're going to look at, I think, for today. When we come back to it on Monday, we will look at coordinates that are in the quadrant. None of these are in the quadrants. These are on the axes. But the ones we'll look at in the quadrants are the 45, the 30, and the 60. And if you notice those 3 points, we're almost missing one. We're missing the 15s, right, to make them all equally spaced. 15 would be about right there, and 75 would be up there. We're not going to do the 15s and 75s until much later. Okay, but we're going to focus on the 45, the 30, and the 60 eventually, but not today. So here are the 6 trig functions along with their definitions as a coordinate on the unit circle. So if I ask you to find the sine of an angle, step 1, you have to find the coordinate for the angle. Step 2, if I want the sine, you need to tell me just the y value. That's the definition of sine. If I ask you for the cosine of an angle, step 1, find the coordinate. Step 2, tell me the x value. So not only do you have to find the coordinate, but you have to know what to do with the coordinate. Does he want the x value? Does he want the y value? Or does he want us to divide them? Okay, in that case, if you're dividing the y by the x, that will give you the tangent of the angle. And the abbreviations for these trig functions are just the first three letters of each trig function. Now, we have three other trig functions. The cosecant, the secant, and the cotangent. We can't abbreviate cosecant COS because we already used that. So they just use the syllables, CSC. And if you look at the formula for sine and you look at the formula for cosecant, what do you call those two things? They're reciprocals. In fact, these are all reciprocals. That's why I set them up the way I did. Cosine is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. So what would cotangent be? X over y, yeah. So a problem that asks you for all 6 trig functions would actually be 6 separate questions on the test. I'm not going to ask you, I'm not going to say, tell me the 6 trig functions of 90 degrees. I would probably say something like, find the cosine of 90 degrees. So first you'd find the coordinate for it, and then you just tell me the x value, and that would be it. When we practice them in class and in the homework, we will do all 6.
Why do you need the theta next to each of them?
Because this is an argument that's being plugged in. It's kind of like if I write this, square root of, and let's just pick a variable, m. The m is the thing you are plugging into the square root function. This is the thing you are plugging into the cosine function.
Oh, that's the 90 degrees.
Yeah, it doesn't mean multiply at all. When you write this, it's kind of like if I said this. This does not mean square root times 90. There's no multiplication in this problem at all. Neither is there here. You're taking 90 and you're filling it into the square root button on your calculator. You're taking 90 and you're filling it into the cosine button on your calculator. So theta stands for the thing you are taking the sine, the cosine, or tangent, whatever, of. All right, so I think I mentioned that to you guys already. Angles that are 0, 90, 180, or 270, those are called the quadrantal angles. And there's really 2 steps to do unit circle trig. Okay, step 1. First, you have to find a coordinate. Now, sometimes the coordinate will be given to you. Let me show you I'll come right back. Let me show you an example. Here's a problem where they give you the coordinate to start with. You don't have to find it. Here's a problem where they don't give you the coordinate. They give you the angle. So in that case, you need to find the coordinate first. Okay? So step 1, find the coordinate if it's not given. Step 2, plug the coordinate into the correct formula. Which formula? It depends on what you're finding. If you're finding sine, you use the y. If you're finding cosine, you use the x. We're going to go through all 6. Okay? So we'll practice all of them. All right, so we'll finish up with just a few examples of doing unit circle trig. It's going to be very easy because it's only going to be coordinates that have 0s and 1s in them. That's it. So arithmetic will be pretty straightforward. All right, so they give me a point. Find the 6 trig functions that correspond to the angle represented by that point. You don't even have to know what angle that represents. I mean, I hope you do. It's 90. But you don't need to know that to do this problem. So let's start with sine. Sine, according to the definition, is what letter? Y. And what's my y in this case? 1. Done. That's the sine. Cosine is which letter? And in this case, 0. What's my formula for tangent? y over x, so if you set it up the way I did, it's basically just like putting a fraction bar right there and dividing them. Y over x. What do you get when you do 1 divided by 0?
Not possible.
It's not possible, it's undefined. Now, to get the 3 that are on the right, what did we say the connection was between the 3 on the right and the 3 on the left? They're just reciprocals. So all you have to do is flip each answer you already have. All right, what would the cosecant of the angle be that's represented by that coordinate? 1. My next trig function that goes with cosine, what's the reciprocal?
Over 0.
What's the name of the function?
Oh,
Secant. And what would the secant of the angle be represented by that coordinate? Undefined. Right? And what's the name of the function that's the reciprocal of tangent? Cotangent. So when you flip 0, you get undefined. So when you flip undefined, you get 0. So that would be 6 separate questions on a test. But I'm probably not going to ask you to use the same coordinate 6 times. I'll give you different coordinates. Okay. Let's try this one. Does that look like any of the coordinates for the quadrantal angles?
No.
Because it's not a coordinate for a quadrantal angle. It's a coordinate for some other angle. Now last time I said you don't need to know the angle, you just need the coordinate, and I said I hope you know what the angle is. This time I don't think you'll know what the angle is. This coordinate represents an angle. What angle? Who cares? The important thing we know is the x value and the y value. That's all you need to know to do this. So let's start with the sine. What would be the sine of the angle represented by that coordinate? John? 3 over 2. What would be the cosine of the angle? Okay. 1/2. And the tangent, just imagine putting a division line right there. What would happen when you divide root 3 over 2 by 1 over 2? Yeah.
Well, the 2's would cross out and you just get square root 3.
Yeah, the 2's would cross out because if you think of it the way that you learn to do it is you take the bottom and you multiply by the reciprocal. Well, the 2's would cancel out. So all we have is square root 3. Okay, and what do I do to each one of those to get the last 3? Reciprocal. Cosecant would be, anybody tell me what the cosecant would be, and if there's anything we're not allowed to do, you need to fix that as well. John?
It would be 4 over 3.
Can you tell me how you got that?
Well, so if you flip it, that just becomes 2 over the 3, right?
Okay.
If you square root it, top and bottom. Let's take over to that now.
So how do we fix that? What do we have to do? Sophie? Multiply top and bottom by square root of 3. So 2 root 3 over 3. So we got the first step right. We got the flipping. But then we just have to fix it. My secant? What would that be? 2. And what about my cotangent? Square root of 3 over 3. Because when you flip that, you're going to get 1 over the square root of 3. When you fix it, you'll have root 3 over 3. Always going to ask for exact answers on these kind of things. No decimals. Okay, questions on that one? Yes?
How did you get cotangent again?
So when you flip the tangent, you start with that. And then you multiply the top and the bottom by the square root of 3. Okay, I don't know if I'm gonna do all 6 trig functions of 90. We'll do some of them. But what's the first thing you have to find here, and you can't do anything until you find it? Yep.
The coordinate.
You need the coordinate. It's great that they gave you the angle, but that's more work. Now we need the coordinate. What's the coordinate for 90 degrees? Yep.
0, 1.
0, 1. Well, look at the problem we just did. We just did this problem. So this is example 1a. The only difference was you had to find the coordinate first and now go through all the steps. All right, let's do 270. What do I need first?
Coordinate.
Coordinate. What's the coordinate for 270? Yep.
0, -1.
0, -1. That's where you go down 1. So now, let's find the 6 trig functions of 270 degrees. What would the sign be? -1. Cosine? 0. Tangent? Undefined. There's not a lot of variety in the answers for the quadrantal angles. The only choices are 1, -1, 0, undefined, every time. Cosecant of 270? Secant? And cotangent? 0. Questions on that? All right. Pi. What unit are they using for the angle this time?
Radian.
Radians, but that doesn't change anything. We still need to find what right away? You need the coordinate. What is pi if you thought about it in degrees? Yep.
Would it be 0, 1?
What is the coordinate?
Oh, would be 180.
That's 180 degrees. And what's the coordinate for 180?
-1, 0.
-1, 0. And now we just fill them in. I'll do the first 3. Y, x, what's 0 divided by -1? 0. We don't want to mix up 0 and undefined. Okay, 0 in the top is okay. Dividing by 0 is not. All right. 6 trig functions of 7 pi over pi. Okay, so what is pi over 2?
9.
That's 90. So this really means 7 times 90. What's 7 times 90?
630.
630. That's kind of a confusing angle to think about because it's too big. What did we say a couple days ago? If you have an angle that's too big, you can do something to it to make it smaller. You can subtract 360. So 630 minus 360. This is the same as 270. We already did 270. So this is the same as example 3. The question looked a little different, but that's just because they wrote the answer in radians for the angle, and then when you convert it to degrees, you end up with the same thing, so it's the exact same coordinate. Yeah.
But isn't 7 in radians though?
Well, this whole thing is in radians, but if you know that this is pi over 2, and you multiply pi over 2 times 7, that's a way to convert it. I mean, you can do it out if you want to do it like this. You're still going to end up with the same thing. Pi's cancel. 2 goes into itself once. 2 goes into 180 90 times. So you're still going to end up with 7 times 90 if you do it that way. How about negative 90? I don't like that angle because it's negative. What could I do to it?
Add 360.
Add 360, and what do I get if I add 360? Yep.
270.
270. This is the same question for the third time. It's just a different way of me asking it. Find the 6 trig functions of 270. Again, see example 3. Same thing. All right. So let me explain what the homework is. On 324, that part's straightforward. It's 56 to 61 and 70 to 73. On 335, I want you to do what they ask you to do in the book for 1, 5, and 8, but then I also want you to do the 6 trig functions of 1, 5, and 8. Okay, so do what they're asking you to do in the book for that, and then find the 6 trig functions of 1, 5, and 8. The sine, the cosine, the tangent, and I'd like you to find the 6 trig functions of these 3 as well. Find the 6 trig functions of 3 pi over 2, the 6 trig functions of 2 pi, and the 6 trig functions of root 2 over 2. That one I'm giving you the coordinate, so you don't have to do that yourself.
Oh, so those are questions you're giving us that are.
These are questions, this 3 pi over 2, 2 pi, and root 2 over 2 one, these are not in the book, they're just ones I made up. And also, let me put the test topics right at the end of the video. Okay, and these are the topics that will be on the test for next week.